Hello friends. In the previous lecture we have seen this material balance in unit operations. We have discussed about material balance in unit operations such as distillation column, absorption column, extractor. We have seen blenders and we have seen crystallization. We have seen drying. Even in drying we have seen much detailed calculation of recirculation of air, all this, right? So now we are ready. If individually a particular unit operation is present, we know how to do material balance in it, right? Now we are going to discuss about material balance in multiple units. That is, if several number of single units are connected in particular fashion, it may be in series fashion or parallel fashion. So how to perform material balance in such multiple units? Okay, so so the objectives of this particular lecture is, we want particular model is to write a set of independent material balance equations for a process involving more than one unit. So it can be as simple as two units, or it may be, even if it is a full chemical plant, we may have more than 5 to 10 units also present in it, right? So the second objective is, once we write the independent material balance, we will able to solve the problems involving several serially connected unit operations or unit processes. Okay, so right, currently we are only focusing on unit operations, because we have not seen what is unit process material balance. We are yet to do it, so we'll do it after this particular lecture. So now we are focusing on unit operations connected in series. Okay, so but the concept is going to be the same, because this material balance in multiple units, it may, because when you have multiple units, the reactor may also be a part of it, right? So that way we are going to consider that thing also here. Okay, so first we should know what is a process flow diagram. Okay, in a chemical industry, a process flow diagram is an important tool. Okay, so that is a diagram actually. So in a chemical process, it is also called as process flow sheet or block diagrams. Block diagram is with simple boxes. If you draw, it is a block diagram. Whereas if it is a process flow diagram, we have to follow certain rules. Also, these process flow diagrams can be as simple as it is, or it can be even more detailed one. Okay, involved including, say for example, process control industries, process instrumentation. Even we can include such minute details of instrument attached to. So, for example, if it's a reactor, if a temperature controlling measuring device is there, pressure measuring device are there. So in that case we may even go for process instrumentation, right? So when you, this process flow sheets are basis for instrumentation engineers to add process instrumentation to the system. Okay, so already in several things we have used these process flow diagrams, right? We are used to process flow diagram in our computer courses, where which we have done a simple flow diagram. There is a meaning for what is the rectangle shape, what is the circle, right? Ellipse size. So each one has its own importance. Okay, so for example, in computer programs, you can see that oval shape is there when it is a terminal point. It may be a start or stop, right? If it is a parallelogram, it can be input or output. In a rectangle, it is process. Diamond, it is decision making. So like that, we have different symbols being used in computer programming, right? So coming to our chemical industries, in chemical industries also, we are going to have chemical process flow diagram. So in simple words, a process flow diagram is a graphical representation of a chemical process. Okay, so it may be unit operation, simply unit operations also, but mostly there will be some chemical reaction taking place, right? So it is a graphical representation of a unit operation or unit processes involved in a chemical industry or manufacturing industry. The help it gives us is, it helps to describe the actual process with sufficient detail. So what is the mass entering the system, each unit, what is the, how much pump, what is the pump attached to it, what type of pump is attached to it, what is the head developed by the pump, what is the energy consumed by the pump. So all this information can be given in a single diagram, which may be useful for doing the material balance and energy balance. So these process flow diagrams are useful to do material balance and energy balance, and they are used to troubleshoot. Say so something is happening, Immediately once we come to the plant, we will first ask for flow diagram. What is happening? Because you are new to your chemical plant. If you want to understand what are the different unit operations present in the system, to understand the system, it is you can quickly go through the flow diagram, and you can understand what each building represents, right? It's like knowing the campus map once you enter into the college, right? So you will easily know where is the ATM available, where is the director office, where is dean academics, where is hostel office is there, right? So where is stadium, where is our cricket ground is there, like that. If you want to know, it's like a campus map. It is how it is helping for a student entering our campus. This process flow diagrams also help us to understand the system quickly. Okay, so that once we know the system, we will able to, it will help us to troubleshoot the things. And if you want to control certain parameters, so it will be used, right? Say for example, police use the traffic map is there, so suddenly there is an accident, they'll go through the map and say this alternative route. How Google map helps us to choose a route, which route to travel if you are traveling from one city to another city. So it will tell us the quickest route, right? If there is traffic jam, if you don't want to go through the toll gates, it will even suggest the route without toll gates. So for that, this map, how map is useful there. Similarly here, process flow diagram is useful for us. We can control the parameters once we know the flow diagram. It will help us to optimize the system, right? So it will help us to optimize the system. Or say for example, one existing plant is there, you joined as a chemical engineer there, and you want to improve the system. For example, it is the current technology that is being used to produce the material is emitting lot of pollution. It is causing lot of pollution to the environment. But if you have a greener technology, green method to produce the same, with where you minimize the toxic emittance into the atmosphere, so you can make modifications in the existing plant, right? So to suggest a modification also, we should show the existing chemical plant what is the alternative we are suggesting, modifications that we are suggesting, how much we have to invest for it, can be explained with such a process flow diagram. Okay, so for example, this process flow diagram, it can be as a simple layman, we can make small empty boxes, right? But to understand technically process flow diagrams, there are different symbols that are being used in the industries. Okay, when you make chemical process industry flow diagram, for example, cooling towers are there. What is the use of cooling tower? The air stream which is being used in the system, we have to cool the air before sending it into the atmosphere. Otherwise, the people living nearby will complain, right? So from the industry, hot air is coming, we are not able to survive here. So in the process, you have used the air, because in reactor system, wherever oxygen is required, you send in air. The reaction may be taking place at 500 degrees Celsius or even 800 degrees Celsius. So the air that is leaving the system will be at very high temperature. So in that places, we have to cool them off. Okay? Before leaving the air into the atmosphere, we have to cool it to room temperature or ambient temperature, right? So that way cooling towers are used. So what is the symbol used for it? In that, different type of cooling towers are there. So all this unit operation we are going to learn in different courses like heat transfer, mass transfer, all this. Okay. Now here the symbols we should know. If you are able to make a flow diagram, we have to use the appropriate diagram representing it. Particularly in this course, we will be using heater. So heater means one. What is the symbol we have to use? Heat exchanger means how to make use of it. Heat exchanger, how it can be represented. Okay, you can just go through this. Okay, it take a few moments to see what are the different. Say furnace is there, breaker is there, crusher is there. It can be mechanical operations, right? U-tube, heat exchanger, air blown cooler. These are mostly heat exchanger equipments representations. And this cooling tower is heater as well as mass transfer is taking place. So mass transfer operations. Okay, so particularly for example, if you are looking at the reactors, different type of reactors are there which you will learn in respective courses like chemical reaction engineering 1 2, catalysis course, all that. Okay, simple drum, how to represent a drum, horizontal drum, vertical drum, packed towers, fixed bed reactors, tray columns, how to represent them in a flow diagram, autoclave reactors, spargers are there, tubular reactors are there, plug flow reactor, CSTR is there, serpentine type tubular reactors are there, open tank, covered tank, how to represent in the flow diagram. We have different flow symbols we have to use. Okay, this particular diagram, for example, if it is mechanical operations, we have clarifier, screening is done, filtration is done, agitators are there. Okay, if there is vaporization taking place, how to represent them. Evaporator, it's a heat transfer equipment. In a spray tower, if you want to express fluid mechanics parts like centrifugal pump mixer, fan, blower, roll press, cooling towers, kettle, propellers, instruments, how to represent them. If it is a simple flash drum, how to represent it. If it is a vessel, how to represent it. So you can see the diagram here. And finally, there will be shipping, right? Means after packaging unit, there will be shipping part. So if to represent shipping, you will use tank car or tank truck. How to represent them. And as I said, even if the valves are used like before the pump or after the pump, there may be valve to allow opening and closing of the flow, adjusting the flow rate. So how to represent a valve. If it's automated motor valve, how to represent it. Venturimeter mean how to represent, right? So like that we have. Similarly, this also line diagrams. You can see CSTR type, different type of unit. If there is spraying is there, you can use that thing. Okay, so for example, so here what is happening, something is being sprayed here, something is used to heat it or cooling it, right? It is a jacketed kettle with CS, with a mixed agitator. So it is a unit where we have different things. It's a cyclone separator. We are having energy input, right? So there are two streams coming in contact with each other where there is heat transfer is taking place. So that way it can be heat units. So packed column, okay, it's a simple vessel in which we have steering arrangement, right? So there can be a mixer and the product bottom can be leaving. Okay, so this is something can be heater. Okay, so there is a one input one output, so some heating is being done. So these are used to represent. This is actually filtration or sedimentation type things are there. Okay, these are some of the symbols for heat exchanger units. Cooling tower mostly represented like this. These are all actually gigantic towers which we can see in our thermal power plants or other power plants. Okay, heat exchangers, shell and tube heat exchangers are being represented like this. Okay, different type of pump like gear pump, positive displacement pump, reciprocating pump, centrifugal pump. There is a way to represent them in the system. So if you look at a chemical plant, they involve large number of interconnecting processing units. So they are represented in using a process flow diagram or process block diagram. Usually block diagram is for our simple calculation purpose, rough work. But if it is actual final output, it has to be in a process flow diagram. Process block diagram we can use in the preparatory stage. But when you are representing them in actual process flow diagram, we have to use the appropriate representations. Okay, so here you can see a process flow diagram of ammonia production. Here you can see, here you have input, air is entering, right? So what are the different content is there? So there is a step where production of the synthesis mixture is taking place. Okay, so then you have a heater. Okay, they have a reactor, so where ammonia is being produced, where you have a water waste heat boiler. Okay, so finally we have a heat exchanger, we have a pump here, compressor here, you have compressor, three compressors are there, right? So like that it gives even a semi-skilled supervisors or laborers present in the working in the company can also understand somewhat basic information that they are looking for from the flow diagram. So what is a block diagram? So this is an example for block diagram for production of hydrogen. As I said, we have been using this kind of block diagram only to solve the numericals, right? To do material balance. For example, we have some basic raw material which is being dried. Then some gasification is taking place in the reactor. Okay, gasifier. So steam is supplied for it. Okay, so we have steam syngas being produced, after which some further reactions are taking place. Okay, so we get hydrogen and powder. So hydrogen is being produced like this. So this way, these are both are representing a production chemical plant. Okay, so here it is a formal presentation. Here block diagram is semi-formal or an informal representation of the information. So essentially, process flow diagram is a drawing which essentially captures the process flow for a processing plant, chemical processing plant or a manufacturing unit. Okay, or in case of pharmaceutical unit, only mixing is there, right? Pharmaceutical, chemical plants, all that. So a PFD, process flow diagram, is used to capture the main process equipments, main process streams, flowing units, then process or design conditions like temperature, pressure at which they are operating, and the basic process control scheme in a single drawing. So this you will learn slowly. That means around the 7th semester, 8th semester, you are going to learn about basic process control. So there, this flow diagram are basic to the flow diagram which already we have done with the material balance and energy balance. We will be adding control parameter. So what is the process control, PI controller, PD, PID controller, like that, different controllers we will be adding to the system. So particularly for instrumentation people, chemical engineer has to provide the process flow diagrams. Okay, so there are various parameters which we should be provided in a process flow diagram, so which you can go through this theory part. Okay, so wherever flow is there, wherever no flow is there, all this should be represented here. Okay, so please take few minutes to go through this theory part yourself. So this is an example typical flow diagram for amine recovery system. Okay, so you can see that at the bottom of the figure some operating ranges are given. What is the regenerated operating conditions? Okay, so we have a sour gas entering. There is a tray column, bottom tray, top tray. So we have a rich stream bottom product is rich in amine. We have a control, it is being returned back, so which is sent to it. It is some preheated somewhere. So this rich amine is entering into the second column. Okay, so again we have the condenser and we have H2S and CO2 acid gas are leaving as the top product. At the bottom product we are getting something which is being condensed. Okay, so we are collecting the condensate. So some lean amine is returned back to the top of this column number 1, like that. So this is a representation of a process flow diagram. Another example I can give is a reactor is there where, let me say, some alcohol is being converted into ether. Okay, so what is happening is some raw material is entering. This is a simple flow diagram for our material balance purpose or energy balance purposes. Okay, so we have a reactor to which the feed containing 85% alcohol, 15% water is entering. So the reaction taking place in this reactor is there. So some recycled product is also entering this reactor. So the product coming out of the reactor stream is sent to some column where the product is being recovered, and from as a top product we are getting the pure ether which is formed. Okay, so bottom product will have mostly water because that is the product here. So whatever the minor quantity, because even if it is a distillation column, so the bottom product also will contain certain amount of alcohol, so or even the unreacted ethanol whatever is there, so that can be recovered. So we can go have a recovery unit from which the ethanol is recycled to the reactor. So bottom product is alcohol with very negligible or very less amount of alcohol is being sent as the waste. Okay, so this represents a multiple unit. So that's what we are going to do, numericals on material balance in multiple units involving unit operations as well as processes. Okay, so this is an example for cement industry. So which here you should able to tell me which one is unit operation, which one is which one is process flow diagram, which one is process block diagram. Okay, so what is there in the left hand side is process flow diagram. Whereas the similar process, both are cement representing operations taking place in a cement industry. Okay, cement industry, rotary kiln mixer is the major instrument. Okay, remaining all are millings, filters will be there, cyclone separators will be there. Okay, so that way, so here also we can represent the same. You can see kiln, rotary kiln here, rotary kiln here, calciner here also. Okay, so that way, so we should know the difference between process flow diagram or process block diagram. Okay. Now let me tell you how many material balances equations can be written, how many individual material balance can be written for a process. Okay, so what we are going to discuss here. So, let me consider a system. So we have considered a system. What happens is, let me say there is a stream number 1 and here raw material 1, raw material 2, which are mixed together and being sent to this unit. Okay, so A, let me say, is a reactant A, a reactant B, or it may be simply a material a liquid or two liquid streams which are mixed and sent to the system, and there is another material which is being a stream which is also entering the system. And what happens is, what we get out of it is a separator. I think already we have discussed about drying. Okay, so this is similar to that. Means recycle air is being mixed like that, we have seen, right? So this is also some similar to that only. So from the 5, so we had a stream with 5 and which is being sent into a separator where we get two different streams. Okay, so we have one. So we have a stream 1, we have stream 2 getting mixed, and we had a stream 3 and we have a stream 4 entering here. So something is happening here. It may be unit operation or process. Okay, it may be unit process or unit operation. So what is happening here? So this is entering. This the product stream is 5. Okay, let me say stream 1. So this is stream 1. So this is stream 2. So after mixing we get a stream 3, right? So we have stream 4, we have stream 5, we have stream 6, we have stream 7. So there are 7 thing is there, different flow rates. One is stream 1 is a flow rate of certain component. Okay, so if you consider this is how to do overall material balance for this system. How to do overall material balance for the system? So how to do, or how many inputs are there? How many input is there in this system? So here input streams are 1, 2 and 4. These are input streams. What are the output streams here? Output streams are 6 and 7. Okay, so we have input streams 1, 2 and 4, output streams 6 and 7. Okay, so that will represent us, so that way we can consider the unit as, so overall material balance can be done in this version, right? So there are 3 input, there are 2 output. When you consider the whatever individual units are there, what is that? Mixer, then we had a system unit operation, right? So then we had a separator, right? So there are 3 inputs. So we have stream 1, stream 2, stream 4, stream 6 and stream 7, right? So what we can consider this as a single block. So that's what simplifying we are doing. So this totally can be considered as, I will represent it as, there is stream 1, stream 2, stream 4 giving stream 6 and stream 7. So this can be whatever may be there. There may be different units may be there, but what I have considered them as a single block. Okay, so I have seen overall how many inputs are there into the system, this system. So into this system, how many inputs are there we have seen, and how many things are outputs are there we have considered. So that way we can simplify this and write the overall material balance by considering this total units as 1. Okay, so there is another way of doing the same. Means like this we can write one equation, right? So we can write overall material balance by considering this for 1, and we will get a one expression. Okay, one equation is obtained. Okay, so we know that we have seen what is degrees of freedom in material balance: number of equations and number of parameters or number of unknowns, right? When the difference is equal to 0, then only, that is the number of equations and number of unknown parameters are same, we have degrees of freedom equal to 0, which we can proceed to solve the problems, right? That we have discussed in our earlier lectures. So now another way to look at it is, we can even consider this mixture is there, this part is there, right? So we can have here, what is the two inputs? We have 1, 2, 4, right? So this can be considered as a one unit, and we can do a material balance across this mixer and this operation. Okay, so that is, let me say 2, and I can do a material balance separately for this mixer, right? Then this 4. Okay, so this can in a diagram, if it is overall, I can consider this as one, this can be considered as 2, and this can be considered as 3, and still we can write a material balance, right? For one, for this what is the material balance, for this what is the material balance, right? So as per the need, we can write any number of equations by considering several streams individually or collectively or overall. Okay, so now we will do a numerical. Oxygen is produced, take down, I'm typing for you. Oxygen is produced by liquefying air and distilling it at low temperature. In a particular installation, 2 distillation columns are used as shown in the figure below. All the compositions are reported in mole percent. Calculate A, the percentage recovery of oxygen in the oxygen rich product stream. B is the flow rate of stream 1 for 10 mole per second of product oxygen stream. So this is our question. I repeat, oxygen is produced by liquefying air and distilling it at a low temperature. In a particular installation, 2 distillation columns are used as shown in the figure below. All the compositions are reported in mole percent. Calculate the percentage recovery of oxygen in the oxygen rich product stream. Second part is the flow rate of stream for 10 mole per second of product stream. That is the flow rate of stream 1 for 10 mole per second of product stream. Okay. So what the diagram is given, take down this diagram. have unit operation, distillation unit, right? Two distillation units are used. So you have a feed, that is liquefied air. I am writing extra here. Okay, this is our feed F. Okay, so liquefied air containing 79 percentage, 21 percentage nitrogen and oxygen. Why I have written it? It is given that air. So we know the composition of air. It is not given. So we know what is the composition of air. Okay, so it is given that there is a product stream. This is here. We have another stream. So W stream is there. There is one oxygen product. Okay, so which is given 10 mole per second, and the composition is given 99.5% oxygen, 0.5% nitrogen. So we have stream 1. This is stream 1. This is stream 2. So they are given stream 1 is 60% nitrogen, 40% oxygen. So here we have 96% nitrogen, 4% oxygen. Okay. So we have a feed stream. So we have distillation column 1. So top product. So we have S2 stream 2, which is 96% nitrogen. Okay, deeply more appropriate to show like this. Top product, bottom product, right? So if it is distillation column, we have a distillate, we have a residue. So whatever is coming, two streams are there. Again, both they are sent to distillation column 2, where we are having this thing. So question is, what is the percentage recovery of oxygen in the oxygen rich product stream? Percentage oxygen recovery we have to find out. Okay, so how to proceed with this problem? So different data is given. Okay, so what is the overall material balance? We have a stream, different streams are there. I will just write a summary here too, so that I can make use of them easily. Okay, so we have nitrogen, oxygen present in feed. What is that? Just now I wrote it, right? 79% nitrogen, 21%, all are mole percentage, right? Okay, all are in mole percentage. So that is the composition. Stream 1 data is given 60%, 40% it contains this, and we have stream 2 96%, 96% and 4%, right? So then we have oxygen product stream, right, which has 99.5% nitrogen. Look at the diagram. So in oxygen product stream, it is 99.5% and 0.5%, but not this thing, right? Oxygen is so we have oxygen is 99.5% and nitrogen is 0.5%, and we have W stream which has 98% nitrogen and 2% oxygen. So these are the composition data we have. Question is, find S1. First let us find out S1. Okay, so how to proceed this? For unit 1, For unit 1, what is the overall material balance? Overall material balance for unit 1 is F equal to S1 plus S2. S1 is given 10 plus W. Okay, this is equation number 1. What is the oxygen balance, individual material balance for oxygen? So the mole fractions of oxygen is 0.21. 0.21 into F is equal to, so this is 40 percentage, that is 0.4 into S1, 0.4 into S1 plus W has certain percentage, right? So what is W here? 2% oxygen, right? Within the first unit, right? Stream 2 has 4% oxygen, so that is 0.04 into S2. So this is equation number 2. Then overall material balance. What are the overall material balance for oxygen? Overall oxygen balance. What are the units? There are one unit, that is F is the input. Outputs are, there is W and there is 10 product, oxygen product, right? So there are two input and one input in which oxygen is there. W we have oxygen, and in the product also we have oxygen. So we can make the material balance for oxygen overall. So if you write overall balance for oxygen, so what we get is 0.21 into F is equal to 0.02 into W plus 99.5 percentage is oxygen. So 0.995 into 10. Let it be equation number 3. Okay, so we can replace here any W by F. What we can do, from 1 what we have is W is equal to F minus 10. Okay, so substituting 4 in 3, so what you get is, so this for W we can substitute here, right? So substituting this, so you will get the answer for F value. 0.21 into F is equal to 0.02 into F minus 10 plus 0.995. 0.995 into 10 is 9.95. So simplifying, we get F. Solving it for F, we get the value for F, this much moles per second. So what is the value? Please use your calculator. Let me know the value. We get F value is 51.32. Okay, let it be 5. So if we have 5, we have 4. So 5 in 4 gives value W equal to, F is 51.32 minus 10, which is 41.32 moles per second. That will be equation number 6. So we have determined F value 51.32, W value 41.32, 5 and 6, right? So let us go back to equation number 1. So in the unit 1, what we have written is, so here what we have written is, we have F equal to, let it be 1A, F equal to S1 plus S2 also equal to 10 plus S1. This is with respect to overall unit, this is with respect to unit 1, this is for overall unit. Whatever F is entering equal to 10 is the product given, W is the top product. So now we have F value, so we can express these S1 and S2 in terms of S1 or S2 in terms of other, right, each other. So that's what we are going to do now. So we have, earlier we have F equal to S1 plus S2, which is 1A, right? So we can write what is S2. S2 equal to F minus S1. Okay, so what is the F value? F value we have determined from 5, let it be 1B, 5 in 1b gives us 51.32 minus S1. We have S2 is equal to 51.32 minus S1. Let it be equation number 7. Also, we have this equation 2. Substitute this 7 in 2. What is our equation number 2? 0.21 into F equal to 0.4 into S1 plus 0.04 into S2, right? So that is equation number 2. So if we substitute that value, what is that? 0.21 into F equal to 0.4 into S1 plus 0.04 into S2. Okay, so for S2 you substitute equation number 7. For F we have value, right? So S2 can be written in terms of equation number 7. Okay, so substituting, what you get is 0.21 into F is 51.32 equal to 0.4 into S1 plus 0.04 into 51.32 minus S1. Okay, so we have expression now in terms of S1. Simplifying, we will get the value for S1, this much moles per seconds. Okay, so once you get the S1 value, you can find out what is S2 also. Okay, so but the question here is, what is the flow rate of stream 1? That is the one answer for question. Flow rate of stream 1 is this much moles per second. So that is the answer for part B. We have to find the answer for part A also. Part A, what is part A? It is percentage recovery of percentage recovery of oxygen. Okay, so what is there for that? What is that percentage recovery? It is amount of oxygen in product, that is oxygen rich stream, divided by amount of oxygen in feed. What is the amount of oxygen present in the product? It has 99.5%, right? So 0.995 into 10 is the amount of oxygen present in the oxygen rich stream, 10 moles per second, right? Similarly in the feed, now we have determined F value, right, which is 51.32. that is our F value, and it contains certain amount of oxygen. We know air contains 21 mole percentage of oxygen. So this gives us, so actually what it is, actually X of oxygen in the product into total product divided by mole fraction of oxygen in the feed into total feed, right? So this is what we have substituted. This all mole percentage is given, P value we have, it is given in the question, F we have determined, so we have substitute, and it is asked in percentage, so multiply by 100 to get percentage recovery of oxygen in oxygen rich stream is 92.84%. that is the answer for part A. Okay, so part B answer we have already written. What is the flow rate of stream 1? So what is the answer? Flow rate of stream 1 is 24.23. Here it is 92.84. So that is the answer for this question. Okay. So we will do numericals on material balance in multiple units. Okay, so take out this problem. An acetone recovery system having the flow sheet as shown in figure. Acetone recovery system is having the flow sheet as shown in the figure. All concentrations are in weight percentage for both gases as well as liquids to make the calculations simple. And if G is equal to 1400 kg per hour, calculate the values of A, F, W, B and D per kgr. So there are different flow streams. G also there, but the G value is given 1400 kg per hour. And we have other streams like A, F, W, B and D per hour, which we have to determine. Okay. So this is the diagram shown below. So we have a feed. So we have a input stream. Okay. So here we have a input stream G. G is equal to 1400 kg, and it has a composition of air equal to 0.95, and we have acetone equal to 0.03, and then water equal to 0.02. So total should be equal to 1, right? So it is mole fraction. So total mass fraction should be 1. So it is given G equal to 1400, composition is given air 0.95, acetone 0.03, water 0.02. So this is the gas inlet, right? We have gas inlet here, and there is a gas outlet. So this is the gas outlet stream, which is given by A kg per hour, and its composition is given air is 0.995, water is 0.005. Okay, and there we have liquid inlet, right? So liquid input equal to water, pure water W kg. That means other components are 0, only water is present in it, right? So pure water is mole fraction is 1, so mass fraction is 1%, sorry 1, that is 100%. Okay, this is 100% water. The pure means 100% water. Okay, and we have liquid outlet, liquid output out of this absorption unit, which is given as F kg per hour, and most mass fractions are given 0.19 and water. There is no air in it. Okay, so whatever is the amount of air entering here, that should be leaving here. So these values are equal. Okay, that is amount of air present in the gas inlet is equal to amount of air present in the air leaving the system. Okay, and coming to the second unit, so whatever is the output of this unit 1 is being the feed to distillation unit. So we have a distillation unit, so we F kg per hour is given, which is the liquid output from this, and the mass fractions are given. So we have a distillate D kg per hour. Okay, so we have acetone fraction is mass fraction is 0.99, that is 99% acetone and 1% water. And here bottom product from the distillation unit is B kg per hour. Okay, and the mass fraction of acetone is 0.04, that is 4%, and it contains water 96%. So these are the data given. So what will be our basis? This is 1400 kg per hour. So we have to choose a basis such that all the data are in simple values like 1400. So that G value is 1400 kg. That is our 1400 kg. Okay, so that is our basis. So you can find out what is the quantity of air, what is the quantity of acetone, and what is the quantity of water, right? So do the material balance and equate the amount of air present in the gas inlet equal to gas outlet. So like that you have to try to find out all the values. What we have to find out? We have to find A value, F value, W value, D value and B value. So okay, so these many values we have to find out. Composition of each one is given. Okay, so it's not be it's a straightforward numerical, we should able to solve it. Okay, so how to start with? So the composition of gas is given, so we will take a basis of 1 hour, so that G is 1400 kg. So and we take G value is 1400 kg per hour, so that when we take basis of 1 hour we get G equal to 1400 given data. So this is the mass fraction, so this is the kg. So 1400, how we get is 1400 into 0.95 is this value. Okay, 1400 into 0.03 is this value. 1400 into 0.02 is this value. So we get the amount of air entering the gas, entering in the gas we can determine, acetone amount entering, water entering. These three we have calculated, and along with this we have W kg of water entering. So there are 28 kg of water entering in this G, and along with it W kg of water is entering. Okay, so with all this we should be able to write the overall material balance and individual material balance from this diagram. Okay, so what is the overall material balance? You can see here G is inlet, W is inlet. G, W and A, these three are inlets, right? G, W are inlets and A plus F is inlet. A is the output, F is the output in unit number 1. If I write the material balance for first unit, material balance, overall material balance in unit 1, so we have overall material balance equal to G. So we get overall material balance is G is the input, W is the input, A is the output plus F is the output. Okay, let it be equation number 1. We have 1400, G value is given 1400. So I can write 1400 plus W is equal to A plus F. So let it be 1A. Then if you write the individual material balance for air, as I told, amount of air present in the gas entering is equal to amount of air present in the gas leaving the system. So we had 0.95 into G equal to 0.995 into A. Okay, so now we can write it for acetone. So if we write for acetone, what is the amount of acetone present? Remember, acetone is present in the G entering and the product that is leaving. So whatever is the amount, that is equal. It is not going along with the gas, right? So that way 0.03 is the percentage in the gas entering. So G value we know. What is the G value? 1400, right? So G value we know 1400 into 0.03 is equal to 0.19 into F, right? And similarly, if we write the individual material balance for, we are writing individual material balance for acetone. Then if you write individual material balance for water, so what you get is the feed contains, you see here, the feed is containing 0.02 percentage water, 0.2% water, 3% acetone. So that's how we have written this material balance. So 2% of water, 2% into G, that is 0.02 into G plus total kg of water entering. This is the total amount of water entering the system, which is equal to A contains 0.5% water. That's why 0.005 into A plus the F contains 81% water. That's from the block diagram we have, right? So given data. So here it is 81% water, here it is 0.005% water. Okay. So that way we can write the individual material balance for water, 0.005 A plus 0.81 into F. Okay. So now we can write from equation 2, 0.95 into G plus 0.995 into A, right? G value we know. Okay, so G value is, you know the G value, so you can write 0.95 into 1400 equal to 0.995 into A. Simplifying, we get the value of A value, right? So you can use your calculator and check whatever answer you are getting. So we get A value like this. Okay. Similarly, from this equation 3, we have 0.03 into G, which is 1400 equal to 0.19 into F. So simplifying equation 3, substituting the value of G, that is 1400, we get F value. F equal to 221.1 kg per hour. So that also, after simplifying, we get the value of F. Now equation 1, you see, now what we have calculated the value of A, we have calculated the value of F, G value is given. So from equation number 1, we can get what is the value of W. So that is 1400 plus W equal to A plus F. Therefore W is equal to, substitute the value of A and F found out here, right? So let it be 5, 6, we will get the 5 and 6 is 1, we get the value of W, which can be written as 7. Okay, so we got the value of W, right? So this is with respect to unit 1, we have calculated all the values. Now moving on to unit number 2, whatever F value we have determined here as 221.1 kg per hour, that is the feed here. That is the feed to unit number 2. So we are concentrating on unit 2 now. From unit 1 material balance, individual material balance, we got the value of F equal to 221.1 kg and the composition is given 19% acetone, 81% water. You can calculate the value to be 0.19 into 221 is 42, 0.81 into 221 is 17.9 kg, right? So 42 kg, 17.9 kg are the amount of acetone and water present in this system. Now with these parameters known, we have distillate D is D kg, composition is given 0.99 into D is the amount of acetone. Amount of acetone is 0.99 into D. Amount of water is 0.01 into D, right? Similarly here acetone amount is 0.04 into B. Amount of water is 0.96 into B. Can you make a material balance for acetone? Make a material balance for water. We can find out the required values. What is the overall material balance here? The overall material balance here is F equal to D plus B, which gives D can be written as, or B can be written as F minus D. F value is known, we have found from unit 1 material balance, 221.1 minus D, right? So let it be a now give a number for this equation. This is overall material balance. Then if you write the material balance for acetone, can you write the material balance for acetone? So what is that? Acetone material balance. Acetone material balance is 0.19 into F equal to 0.99 D. Remember 0.19 into F equal to 0.99 into D plus here acetone is 0.04 into B, right? Plus 0.04 into B. But what is B here? We have an expression, right? Substitute this in this equation. B value can be written as, you can write 0.19 into F equal to 0.99 D plus 0.04 into 221.1 minus D. Okay. So here we have only unknown parameter is D. Simplifying, we get D value. Okay, you can determine the value. Please proceed. What is the D value? So I repeat. First what you have written is overall material balance F equal to D plus B. Rearranging P equal to F minus D. F value is 221.1. So we got B equal to 221.1 minus D. And if you write the individual material balance for acetone, we have 0.19 into F equal to 0.99 D plus 0.04 into B. Refer to the diagram and write this. Okay, and the value is 42.99 D. Okay, and we get the value of D here. Okay, 0.99 D plus 0.04, we get the value. Okay, so we get the D value as 34.91. Okay. So we get the D value is to be 34.91 kg per hour, right? We get the D value. Now only unknown parameter is B value. So how to get B value? B value is F minus D equal to 221. B equal to F minus D. So F value is 221.1 minus D value we have found out to be 34.91. Therefore 186.2 kg per hour is the value of B. Now we have almost determined everything. So write down all the values. A value we have determined to be 1336.17 kg per hour. F value we have determined 221.1 kg per hour. Okay, and W value we have determined it to be 157.8, and D value just now we have determined here. So we get D equal to 34.91, and finally we got B value, which is 186.2, okay, kg per hour. So now all the values are there. We have to verify it once. Okay, all the values are there, A, F, W, D, B. Now we can verify it in overall material balance at least. So we can do it in G plus W equal to A plus F, right? So substitute LHS value, substitute RHS value. If LHS is equal to RHS, then verified. Okay, you can say it is verified. So verification is G plus W equal to A plus F. Left hand side value is 1400 plus 157.8. Total comes to be 1557.8 kg. Right hand side is 1336.7 plus 221.1, which is 1557.8. Since LHS is equal to it is verified. Okay, you can even do a individual material balance and verify those things. Okay, so that's what we have done in this problem. Okay, so what we have done in this problem? In this problem, two units are there. One is absorption unit, another one is distillation unit, and G value is given to be 1400 kg per hour. That is the only parameter given. Okay, so the composition is given air, acetone, water in the feed. Here pure water is entering, so there is no need of W kg is given. Air leaving is A kg per hour, F kg per hour, distillate is D kg per hour, bottom product is B kg per hour. We are asked to find A, F, W, D, B. Okay, so first we consider the unit number 1, in which we have done the overall material balance and individual material balance to find the value of W, A and F. Okay, so first we have determined W value, okay, F value and A value. So these three, A value was found to be 1336.7, F value is found to be 221.1, W value is found to be 157.8. Okay, and then we moved on to unit number 2, where this F value is now determined from the previous workout in unit 1. F value was determined and the compositions of all the three streams are known. We wrote the overall material balance F equal to D plus B. So B is equal to F minus D. F value is 221.1. So we wrote B equal to 221.1 minus D. Acetone individual material balance for acetone was written, which is 0.19 into 221.1 equal to 0.99 D plus 0.04 B. So for B is replaced with F minus D, that is 221.1 minus D, and an expression in D was obtained. Simplifying, we got the value of D. Okay, so once we got the D value, we substituted in the equation to get B value, which is to be found to be 186.2, and all the values are reported: A value, F value, W value, D value and B value, and we verified it by substituting in overall material balance, and we got the left hand side equal to right hand side. Okay, thank you. In this lecture, we have seen what is the significance of chemical process flow diagram, what are its usefulness, how this chemical process flow diagram is useful for various applications. Okay, so we have seen the difference between a chemical process flow diagram and what is a block diagram, when we have to use flow diagram, when we have to use block diagram, which we have discussed, and we have done two numericals on material balancing multiple unit systems without chemical reaction, right? Without chemical reaction, we have considered two systems. Okay, so multiple unit system. So actually, we have only considered two unit system in this case. It can be even further more. So once we understood how to do material balance in individual units, it is easier for us to solve the overall problem. When you have a big issue, you try to find out small issues, then you fix one after another, you try to solve the overall issue, right? Similar to that, here also, if you are able to do individually in each unit, if you are able to solve the material balance, then it will be easier for us to solve the material balance for various units present in series or in parallel. Okay, so we will do some more numericals in the next lecture. So if you have any doubts in this lecture, please contact me. And for the next lecture, you are supposed to have completed this lecture before coming to next lecture, because it is going to be continuation of what we have learned in this particular lecture. So please complete this lecture and try to solve all the problems, practice it yourself. And if you have any doubts, please contact me. Thank you for joining my chemical process calculation course. It's bye from 9th year. Thank you.